Okay, so we're going to move on to some more new topics today. But first, what I've done here is I have set up a very brief program. Let's get this thing open real fast for us to use as a way of getting some practice for our assignments. In fact, this could be our first assignment. It'll be very quick and easy. It'll give you a chance to get your hands on VBA. So let's see. Hold on one second. All right, so it's called MA6550 migrate. Now, one thing I do want to point out here, this is something that we need to know before we go any further. Um, Excel, of course, is where we're writing our VBA code, but Excel, it's the standard Excel format .xlsx is not compatible with VBA because it perceives the macros that we're writing or programs as viruses, and it basically will not execute them. So here's what we have to do. There's another format we can use with Excel. So let me open up my notes real fast. So when using VBA, do not standard .xlsx format. That's the one used most of the time with Excel. In fact, you may not even notice it because you use it by default. Anytime you save an Excel spreadsheet, it's almost invariably XLSX. It's possible you have some older ones from quite a few years ago. It's .xls without the X, but it's almost certainly that virtually all of these spreadsheets use end with that .xlsx. So it does not work well, if at all, with VBA programs. So what do you do instead? So if you open up this one that I'm about to show you, the format is listed here as Microsoft Excel macro enabled worksheet. And the extension, oops, I just opened that, is .xlsm. Let's see. Now, if you save a new blank spreadsheet, let me just open up a blank one. So you can see when you save one, you do have an option. You probably never noticed it before because you never really needed it. File, save as. And let's say that you just pick any random name. I just want you to illustrate you how this works. Let's see. I guess this is good enough. So I could call it, let's say, new. And if you notice, it says Excel workbook, of course, fine, that's a standard default type. But if you look at this list, you'll see there's quite a few others to choose from. Excel macro enabled workbook. And that's, well, it doesn't show it, but it's .xlsm. Okay, so make sure this is the format you're using for any spreadsheet that you intend on using VBA with. Otherwise, you're just going to have nonstop problems. Okay, so that's one thing you need to know. And so when you save it, every time if you work on it, save it, it'll just make sure it stays in this format. So another thing you have to know is that even then, the Excel spreadsheet is searching like crazy for viruses. And it has security settings that you need to know about. So like this one, which is where we'll find the program we'll be looking at right now. It is in the proper format. It is in the Excel. Again, there it is. I can't believe it was so hard to find this. XLSM, M for macro enabled. Okay, so in other words, and of course, and once again, that stands for macro enabled workbook. Now, even then, here's what we have to watch out for. If you come into here, I'm going to show you where developer is. Here's the Visual Basic. Now, here's macro security. And macro security can be set to tell it to disable all of your VBA code. You are the one who has to decide how much you can trust VBA. So the first thing you have to do is click on Trust Access to the VBA Project Object Model. And then your safest bet up here is to say disable VBA macros with notification, which means if it sees a macro, which remember is a subroutine, it will try to stop it from running it, but it will ask you what you want to do about it. Okay. If you have this one on, disable VBA macros without notification, it won't run any VBA code and you'll never know why. Now, this last one is probably not safe either because it says, go ahead, run everything with VBA. Because the problem with that is you never know when you might actually have a virus. You don't want to run that. So the best bet here is to put disable VBA macros with notification. That way you can decide, is this for real or is it, potentially something dangerous? All right. So anyway, with all that being said, Visual Basics. So we've got two modules here, as they're called. Module 1 contains a program we saw yesterday, function migrate, average as single, as string, meaning you're reading a single precision variable into the function, and it spits out a string, which is a letter. So it makes a decision based on the else if statements. And so if you want to run this thing, you can go back to the spreadsheet, close and return to Excel, and here's how you invoke that function. Equals migrate. Now, as soon as you start to type it's going to say, listen, here's all these different functions you have access to. Do you mean one of these? You know right away which one is yours because it's not all uppercase. Notice how it says lowercase, or at least partially lowercase. So that way, if you forget, you can just choose it. And now the only unfortunate thing is it doesn't remind you what information it needs. If it's an Excel function, it'll have a little word in there. It'll say, oh, by the way, you need this, this, and this to make this work. If you're using your own functions, you have to remember yourself what belongs in there. You just have to remember what you're supposed to do. So in this one, I'm going to give it a grade of 88. That's my average. And it will say, oh, you mean B. Okay. Now, sometimes you can do this to help yourself make sure your program is working correctly. A lot of time is spent making the program, I wouldn't say idiot-proof, but making sure that mistakes are caught. Like, for example, if you type, because we told the program that the input must be single precision, if you type my grade, and then I try to put in an A, oops, I don't know what you mean. Now, it might accept an integer because it will interpret that as, let's say, 88.0. Okay, so that's fine. It's not quite so rigid about that. But at least you won't accidentally send it, like a letter or something. Now, you can make error testing more sophisticated than that. Like you could tell it what to do with the -10, for example. So the way it was set up, if you notice in the code, it just said anything below a certain level, make it an F. Okay. In other words, anything here, according to what I'm seeing here, and if the average is less than 60, make it an F. Suppose you wanted to make sure that nobody actually puts in a negative number. It could be done. Okay. You could write a routine up here somewhere that says if negative, return or something, return an error message. But here, the way it's set up, anything under 60 will just automatically return an F. So now here's what I would like you to do. Go back in here to Visual Basic. Here's another module that's sitting here. I decided to call it new migrate. You can't have the two functions here that have the same name, otherwise you'll cause problems. So I changed it to new migrate, averages single as string. And so what your job is to take this and rewrite it using um, the select case command. Okay. I did mention this last night. For something that complicated, the else if statements are very useful, but they're a little bit tricky to deal with. Whereas this select case is really set up for exactly this kind of setup. It's perfectly suited for having multiple possible decisions. In other words, is it an A? Is it a B? Is it a C? Is it a D? Is it an F? That's what this is really intended for. So this program could have been written as a select case, and it wasn't. So your job is to turn it into one. Okay, use this as your model and see if you can run it, and then try it. Go back in here when you're done. And since the function's name is new migrated, you would type and then a number. Now, at the moment, the function doesn't exist, so it will not react well to my doing this, but oh, it just didn't do anything. All right, because it doesn't recognize that as a valid function. Okay, so that would be what you want to do. Now, when you're done, you can save this. And then probably the quickest thing to do is email it directly back to me. Now, what probably you should do is this. Of course, I do have a Fairfield email account, but I don't see it very often. So you can either send it to probably your best bet is to send it to my Gmail account. I'll see it right away. Okay. So yeah, send it there. Now, keep in mind that the end of the course is the 15th, which is Friday, but the grades won't be due to the following Monday, let's say. So any assignments that we have, you can basically send them to me, let's say by Sunday night. Let's double check this calendar. I know it's getting very, very late in the course. During the normal school year, we have so much more time to work with the programs, but I wanted to make sure we got all the material done. And so we'll just have a few basic, relatively straightforward programs as our assignments, and that will have to suffice. Um, so let's see here. Let me just double check the day of the week. Right, so officially the last day is the 15th. So, if you could have everything done by the 17th, the night of the 17th, that would be fine. I could then turn in the grades on the 18th. That will work out for you, I think. So this will be the first one. Now the next two, I'll probably have them do something based in the Greeks, which we're about to start now, because they're very straightforward. And then I'm thinking we might do something for Monte Carlo, which is the last topic we'll be covering, because it's extremely interesting and it's kind of it's very straightforward. So um, I think that's what I'm aiming for. Maybe one problem um, revolving around the Greeks, and maybe one that has something to do with Monte Carlo. So at the moment, this is where we're heading. Okay, so but this one is a good way to get your hands on VBA. Remember, learn about how this works with Excel, for example, using an XLSM format, knowing where the code is. By the way, I do want to mention one more thing here. If you wanted to write another program, you're going to have to come over here and type insert module, and that's where you'll put your code. Okay, so now here, I actually entered this part myself. It didn't come like that. It's blank. You have to do that yourself. But if you, let's say you decide to create something called function new product or something like that, x as int. So you notice what it did was it turns the keywords into blue. Part of the reason for doing that is to make sure you're spelling them correctly. And then it automatically provides you with the end function. And then you go ahead and type your code. It would be in here, like you might say, for example, apostrophe this function, signed, take integer, and compute the cost of producing a new product, this many units of a new product, something like that. There's some using apostrophes. The green tells me this is a comment. The program will completely ignore it. You can have as many of these as you want, but once you start it, it's going to be green all the way after that. So what you can do is you can actually put it at the end of a line. Like you could say X represents the number of units. And then you might say something like dim quantity as integer, which maybe you'll use to represent the number of units of the product that you're building or something like that. Dim per unit cost as single. I think it'll allow you to set it to a certain value right off the bat. Let's see. No, it didn't like that. Okay. No, I guess you have to have a separate statement that would say per unit cost equals 100 or something like that. Assuming you already know in advance that that's going to be 100. Okay. Um, Actually, we probably wouldn't set x equal to 0 because that's what's being read into the program. So let's just leave this comment here. And then let's just say that the new product equals per unit cost. Let's fix that. And then for some bizarre reason, let's say it's times the square root of x, and then you'd be done. And in a case like that, you'd have to be careful. You could set it up to make sure that it doesn't accept a negative x, for example. But so now all of a sudden, you've got a real function here, and you can type equals new product. And you notice it's finding it there. And I'll say, well, oops, um, 20. And so what it did was it multiplied 100 times the square root of 20 to come up with that result. Right. So yeah, you can do whatever you want here. You can create all the modules you want, and then you have all these functions available to you. And of course, you can also write them as subroutines or macros if you want. But I think in a case like this, you're probably best off using a function because you're only producing one output. When you need more than one output, like if you're going to produce things like, the grade and then like comments or, things like that, then you probably would be better off with a subroutine or macro. All right. So anyway, let's get back to the new material, which is the Greeks. Now, the Greeks are a set of risk measures associated with options. They're used by traders to determine how sensitive their positions are to changes in underlying variables, which means the variables that determine the price of an option. They're called, you'll see in a second why they're called the Greeks. Now, just a quick reminder, the price of an option, as we saw with the Black-Scholes model, and by the way, it doesn't matter if it's a call or a put. The price of an option is a function of, and that would be the spot price of the asset, strike price of the option, the volatility of the asset, which can be interpreted as the standard deviation of returns to the asset, time until the maturity of the option, and the risk-free rate of interest. risk-free, that would mean the yield of the treasury bill that matures at the same time as the option. Okay, so in the book or in the slides we used typically although sometimes we use K for this one as well. It depends. It depends on what part of the book we're in, what slides we're looking at, but X and K are often used interchangeably to represent the strike of the option. Now, of course, all this implies that if the spot price of the asset changes, all or its constant, then the option price will change. Same is true of volatility, time, and interest rate. Okay, now note, of course, the strike price is a constant, so we can't change. So the Greeks are sensitivity measures. In other words, they're partial derivatives. Meaning, for example, first of the Greeks, known as delta, is the partial derivative of the Black-Scholes model with respect to S. So you can write that in a few different ways. Delta, for a call at least, is written like this. You notice we're using those partial derivative symbols because the call itself is a function of S, X, sigma, T, and R. So we're trying to hold everything else constant. And of course, that's the point of a partial derivative. We're changing S, holding everything else constant. So the Greek delta means how sensitive is your options price to changes in the spot price of the asset. And then similarly, we have one for the put. And of course, this is based on the logic that the put is also a function of S, X, sigma, T, and R. The difference being the magnitude of the change, and in some cases, the sign is different. So as it turns out, we'll see why in a second. Qual delta has to be positive because remember, qual gives you the right to buy an asset. If the asset price goes up, clearly the right to buy it has to go up as well. On the other hand, the put gives you the right to sell. So it stands to reason that when the price of the asset goes up, the value of the put goes down. Okay. Now we can also attach other restrictions on these as well, but just in general, it should be clear that the qual delta is positive and the put delta is negative. Okay. Now let's take a look at this graph. Let me just sketch it out on here for you real fast. This is the payoff to the call option. Okay. We can do this with either the payoffs or the profits and losses. Let's just do this. Okay. I just want to follow along with my graph. So a couple of chapters back, we introduced calls and puts. And this is the payoff profile to the call, which means that as long as we are stock price or the spot price of the asset is at or below the strike price, here the payoff would be zero. Up here, payoff is S minus X, which is guaranteed to be positive. And you can see the slope is one there. But this is the value of the option. This is the payoff. This is also the value of the option on the maturity date. But at any time prior to that, market price is always greater than the payoff until the final date of trading, at which time the two are identical to each other. And as time elapses, the market price gets closer and closer to the payoffs. And on the, like I said, on the final day of trading, they're identical to each other. Okay. So now what we're getting at here is that the delta is nothing but the slope of the tangent line of this market price curve. Okay. Now, based on that logic, and you can see, by the way, the slope is zero. Up here, the slope is one. So that means the market price curve has a slope that's bounded between those two numbers. Actually, what I should say is that between 0 and 1, it can't get any flatter than the payoff profile, and it can't get any steeper either. So in other words, on the payoff profile, the slope is either 0 or 1. There's nothing else. But on the market price curve, it's everywhere, it's somewhere between. And as you notice, as S goes up, the curve gets steeper. And so the delta is the slope of that market price curve. So you can see why it can't go below 0 and it can't go above 1. And then when it comes to the put, so the market price curve there is like this. Now, one thing I do want to mention as a side note, here we're assuming that this is an American put. For very technical reasons, we're using the American put in this case. We'll get back to that later on, but you can see what's happening here is the curve is always negatively sloped. The payoff slope is always 0 or -1. So the curve of the market price curve the slope is bounded between -1 and 0. Actually, I should write it as -1 and 0. So that implies that the delta, because the delta is the slope of that curve, is between -1 and 0. Okay. You can easily imagine why this is so important. I mean, imagine if you have a portfolio full of options, and you expect that, let's say they're all written on Apple stock, and you expect Apple price stock to go up $10 tomorrow. Well, you should have a pretty clear idea of what that's going to do to the options in your portfolio. If you're worried about losing, you'll have to adjust your position, or you can maybe make your position even riskier, maybe not quite so risky, but you have to know what's coming. And so that's why this is so helpful. Now, by the way, this is the equivalent diagram for the European put. The weird part here is that for the European put, there's actually a region within which the market price can actually fall below the payoff. And that's to do with the fact that the option is, in this case, the put is very deeply in the money. And by being forced to hold on to it until maturity, you're actually losing time value. So the slope hasn't changed. It's still a similar slope, but it's just a very peculiar result. This is a very unusual case where when the put is this close, or the stock, I should say, is close to 0, the put's value is so great that it's actually detrimental that we have to wait till the maturity date to exercise it, because if we exercise it now and invest the proceeds at the risk-free rate of interest, it would far outweigh any time value you might capture by holding it to maturity. But basically, as far as the delta goes, you can see it's still a very steep negative value, just like the American version. Now, it turns out we got lucky here. Delta C is approximately equal to ND1. That's all it is. How do you like that? So it's easy to calculate the delta for a call. It's just ND1 from the Black-Scholes formula. And of course, we know that that's part of the process of calculating the call price. We have to calculate ND1 in order to come up with the Black-Scholes price. So when you're calculating ND1, you're almost always, also simultaneously calculating delta C. Now for the put, now this is, remember we did mention that there's two equivalent ways of calculating European put price. One of them is call parity. Of course, remember that one is and then the second one is to just directly substitute. Oh, this one's using K. All right. Oh, this is so annoying. But yeah, this is the strike price. Let's just change it to X, just to be consistent here. Substituting the call parity relationship into the Black-Scholes model produces the following. And so those you can calculate directly. Without knowing C, that is. So therefore, and based on that, so I forgot to write down here, delta C is ND1. Delta P is ND1 minus 1. Okay. So if you remember, this example, we had this a while back where we had a European call option, XYZ stock with a strike of $50, a stock price of 52, a risk-free rate of 2%. We plugged these into the Black-Scholes formula, if you remember, and we did end up with a price of $7.60 some odd cents. But along the way, we showed that the ND1 is approximately equal to 0.6359. And so what that means then is that That indicates that the $1 increase, the price of the stock, and about 63.59 cents to the value of the call, and vice versa too. In other words, if the stock price goes down $1, then so should the call price by about 63.59 cents. Now the equivalent put, meaning the same strike price, the same maturity date, the same asset. So that means that if the price All right, so those $1 increase in the price of the stock is now going to reduce the put price by about 36.41 cents. Okay, and vice versa. Now, again, see the beauty of the setup and is that you can figure out what is the delta of your position as a trader and decide if that's too risky for you or if it's maybe not risky enough. So just keep in mind, here's an interesting side note. The delta of the underlying stock is 1, because that would be so let's say, suppose an investor has 100 shares of stock and 50 puts. What is the delta of this portfolio? That was the same put we just had up here. We have 100 shares of this stock that was mentioned in that problem, selling for $52, etc. But we also bought 50 puts to protect our position. So the delta for the portfolio, which some books use a pi for that, I think holds us to. And you're going to get delta S, which is the delta of your stocks. This is the delta of your P's. Now, you've got 100 shares of stock. And remember, this one is negative 36.41. And so that's going to give us a total delta for this position of 100 minus 18,205. Oops, hold on a second. It's 81.795. Now, that's a pretty big delta, but I mean, it's better than it would have been without those puts. Okay. Now, so in other words, because you have so many shares of stock, if the price of the stock goes up by $1 without any options in your portfolio, the position would go up by $100 because you have 100 shares. But this way, it only goes up by 81.795. And conversely, if the price goes down $1, instead of losing 100, you're losing 81.795. So that really is the purpose of having these puts in your portfolio to protect from downside risk to your portfolio, although at the expense of giving up some of your upside potential. All right, so that I think, oh, by the way, here's some interesting graphs. Here's the call delta mapped against the stock price or asset price. So in this example, the 50 is the strike price. This is sometimes called an S curve because it kind of looks like an S. And if you notice, it starts out very flat. The slope is close to zero. Up here, the slope is close to one. Right around here, the slope is about 1.5. But it's always positive. And so this is the relationship between the delta itself and the underlying stock price. So you can see the delta changes when the stock price changes, or at least when there's large changes. Now, here's an interesting result. The put delta looks like this. They have the same shape. What's different is the signs. If you notice here, here's zero. These are all negatives. Okay. So, actually, I'm sorry, the slope is 0.5 there, but the delta is negative. So now you can see why this is happening, because the two of them are only different by a constant. Now, this, by the way, what you're seeing here will help us understand the next Greek that's coming up. The next Greek that's coming up is essentially a measure of how sensitive the delta itself is to changes in the stock price. In other words, if I have a portfolio full of options and stocks, and the delta is at some level that I'm comfortable with, what happens if there's a huge change in the stock price? Will that affect the delta of my portfolio? The answer is yes. So I have to be very, very careful when I hedge. One day I might think I have a very safe position, and the next day maybe I don't. Okay. By the way, if you're really nervous about what's happening in the market, sometimes traders will take options positions that reduce the delta of the total portfolio to zero. This means that the portfolio is risk-free. It can't change in value. That means it's risk-free, or at least it is for now. So this situation is referred to as delta neutral. In other words, the portfolio is said to be delta neutral when the total portfolio is delta, including the options, that is exactly so. And so sometimes, when got a lot of stocks that you like, but markets are in turmoil, you don't want to sell your stocks, but you don't want to lose a lot of money either. You can temporarily hedge yourself by buying short-term options that bring the delta down to zero. And then when the crisis passes, you let the options expire, and then you can go ahead and continue to make money, hopefully, on those stocks that you own. By the way, what this refers to is what happens over time. Remember, before I said that as time elapses, the market price curve is moving towards the payoffs, and that will affect the Greeks as well. So as time elapses, as we get closer to the maturity date, all of the deltas, no matter where we are in this curve, will also change. Now, what's happening is that The red curve is in the money. That would be, this is in the money. This is at the money, and this is out of the money. The in the money ones are converging to 1. The at the money ones are converging to a half, and the out of the money ones are converging to 0. That's all that this is. It looks very fancy and all, but that's basically all you're seeing. And by the way, the convergence is going in this direction. In other words, time is elapsing from right to left. Okay, be careful with that. Usually you see a time series graph and it goes from left to right. This one is going from right to left. So it ends up, this one is converging to 1, a half, and 0. For the put, it's just the reverse. The one on the top is out of the money. This is at the money, in the money. And of course, remember, moneyness refers to whether or not we would have a positive payoff if we exercise the option. Okay. Now, by the way, remember when we introduced Merton's extension of the Black-Scholes model, we introduced Q to represent the continuously compounded return to the asset. If we're using Merton's model, the formulas for the Greeks are going to be just a tiny bit different. Now, e to the minus qt, if q is 0, like in the original Black-Scholes model, then this expression is just equal to 1. And you'd end up with nd1. If q is not 1, it's going to typically be some very small positive number. And so e is just slightly less than 1. So that means that technically you should take this into account with e to the minus qt. If you leave it out, your answer will only be approximately correct, but this is how you would adjust for the existence of a cash flow to the owner, as we see in Merton's extension of the Black-Scholes model. Now, gamma, this is what I was building up to before. Gamma is essentially the sensitivity of delta with respect to the stock price. In other words, how much does the delta change over time, or as S changes? So it's actually a second derivative. And by the way, this is the Greek letter. This is the uppercase gamma. You don't see this all the time. You see gamma sometimes looking like this. Let's take it backwards 7. Okay, so you can think of it as the second derivative of C with respect to S, or the first derivative of the delta call with respect to S. And then similarly, delta C, or delta P rather, okay, is defined in a similar way. Now, graphically, what you're looking at is the slopes of these two curves. But since they have the same shape, slopes are the same, aren't they? And so it turns out that these two are identical to each other. Because of the way they're defined, they're both going to always be the same. So we don't need to make a distinction between the gamma of a call and a put. So the big question is, what does this graph look like? It's hard to visualize just by looking, but you can see, let's just quickly think about this. The slope of either one of these is what we need. It goes from 0, starts to rise to about a half. And by the way, if you notice the curvature here, it's going from rising, it's rising at an increasing rate, then it hits this point, which is an inflection point, and then turns back down again. So in other words, the second derivative is going from positive to negative. And so the resulting graph looks like this. Oh, there it is. Okay. You can see it's zero, positive throughout, peaks out right around the strike price. The slope here is positive. Over here, the slope is negative. That's your gamma. And it's the same for both calls and puts. All right. So this means that if I have a portfolio that's heavily hedged with options, if there's a significant change in the stock price, the deltas could be affected, and that means my position could either become less risky than it was before or more risky. This gamma will tell me which one it is and how much. So it's like waiting for a storm to arrive. You want to know how much insurance you have. You know, it's kind of like it's trying to protect your portfolio or show you how much protection your portfolio really has. Now, its behavior is it always is going to converge to zero, no matter where it starts out. Actually, no, I shouldn't say that. Sorry. Um, as long as it's not at the money. At the money is a very peculiar case. At the money spikes up as we get closer to the maturity date because we're not sure whether the option will finish in or out of the money, in or out of the money, I should say. So these two are going to zero. This one will eventually reach zero, but at first it spikes up until we find out eventually if the option ends up finishing in or out of the money. All right. By the way, what you're seeing here are the formulas you would use to actually calculate these. These are the remember the deltas. The deltas were easy. The gammas are a little bit messier. Um, oh, and this one, yeah, this is assuming that we have this Q. If we don't have a Q, it'll just be n prime of D1 over S sigma square root of time. Now, what is that prime doing there? Well, this is how we have to think about it. Here's the standard normal curve. And let's say here's D1. We know this. N prime of D1 is actually the height of the curve at this point. And so you can think of it as the marginal change. Shows the um, impact on ND1 of a change in asset price S. In other words, if D, not sorry, D1, but that, in other words, it's D1, but only indirectly through the value. If S changes, D1 changes, and then that affects this curve. So it means like how much of a change is there on this probability if we move up and down that curve. So it's very difficult to visualize what this is telling us. It's the incremental change or marginal change in the probability of Z finishing less than or equal to D1 when there's been a change in S, which in turn triggers a change in D1. Okay. Anyway, that's the formula. And by the way, you can see why, as an interesting side note, This ND1 is guaranteed to be positive. S is positive, sigma is positive, radical T is positive. So therefore, must be positive. Okay. So that helps us understand why the graph looks the way it does. Okay, now there's also several other Greeks. By the way, I do want to point out the ones we're seeing here, the standard ones, there's actually a lot more. We're only looking at the basic ones. If you look in 6C, we're going to introduce a few more. The delta and the gamma are by far the most important. We also want to briefly look at theta, which tells us how much the time value of the option shrinks as we get closer to the maturity date. We also have vega, which ironically enough is not a Greek letter, somehow got chosen for this, probably because it starts with a V. And so often we use, instead of the only other Greek letters that usually you see here, like this is actually lambda. Some books use lambda to represent the vega because of course there is no corresponding Greek letter. And some books use kappa. So that there is a symbol there. But this represents the sensitivity of the call price to changes in the volatility. And then this is the equivalent version for the put. And then the last one of the Greeks that we'll be seeing here is the rho, which refers to how much the option price changes as a result of changes in interest rates. Okay. Now, these three are not as important, but we want to briefly look at them and understand their properties before we move on to really what is a hugely important topic, and that's our discussion about how to price American options. So because it's so complicated, we won't be doing any assignments based on that model, but we do need to understand how it works and how it's different from Black-Scholes. Okay, and then at the end, we'll have Monte Carlo simulation, which is a statistical methodology that's used to simulate the prices of very complicated options. It's not normally used with European or American style options because it would be kind of overkill, but it's saved for a special class of options known as exotic options, where the properties can be very, very bizarre. Okay, so it's a very interesting subject. All right, anyway, so let's see. I guess we can save this until the next time. We'll just briefly touch on these last three Greeks, and then we can spend a lot of time with the binomial option pricing model just to make sure we understand how it's different. I mean, the bottom line is it has to allow for the possibility of early exercise, and that's why it's so much messier than the Black-Scholes model. All right, so yeah, I guess we can save that for next time, and so soon enough we'll be done with everything, and then I'll let you know what other assignments we should do. I thought we might try one or two based on the Greeks and possibly Monte Carlo because they're very straightforward. All right, so I'll see you next time.